Okay, George, you're on.
Hey, good evening, everybody. Welcome back to Conant Show. This is Conant Show 26, and this is the January 18, 2017. And Bob Lavaggi has come back. We're following up from last week, and we have a nice little one of his video shorts on some of the theoretical sciences that he's exploring. And before we jump into that, I just want to update you on my imbroglio with Ulster County and the accuser. This evening, I stopped in over at the Saugerties Justice Court to observe the proceedings against my partner and her new attorney, and was actually quite entertained because in the explorations of the condition of the case, the new attorney, who wasn't appraised of anything fully yet, learned a few things from the prosecutor, which we had been claiming, or I had been claiming mostly, but we had been claiming for a long time now, which is there is no evidence. And this is a remarkable thing here, because the prosecutor admitted to our attorney, and he admitted this to us, that in fact there is no physical evidence. And actually he was practically crying in tears of laughter, because the situation is so ludicrous, and it should have been dropped a long time ago. And we found out also, I don't know how truthful a statement this is, but the prosecutor has been hounded relentlessly by the accuser and is afraid of her. And this is, we find absolutely astonishing that the prosecutor is afraid to drop the charges because of repercussions of the accuser. Never mind the repercussions of our side of a camp, where we're looking at false arrest, we're looking at fraud upon the court, we're looking at misprision of felony, we're looking at unlawful entry and home invasion, robbery. We're looking at a list of offenses against us that is longer than my arm and my leg put together. So anyway, I just thought I'd let you all know that in this proceedings that have been going on for 14 months now, the prosecution has no physical evidence, and the tangential evidence, or the intangible evidence and witnesses and such, have also been voiced as being somewhat on the south side of credible.
Shaky side.
Yes, on the shaky side of credible. So we're going to continue to fight on all the different fronts to get these charges dismissed with prejudice. And now that we are involved with a civil suit against us for $500,000, we're taking it two different ways. My partner has elected to seek dismissal of the case, and I have elected to sue for everything she's got, for the harm that she has done to me and to my loved ones. So that's the update. And as we move forward with our show tonight, I'd like to honor and thank Paula Gloria Barton once again, such a lovely mentor to have, for teching for us as we limp along. We had two cameras for 45 seconds, and then one camera just went blank. So we're back to one camera again.
But great talent.
And great talent. And one other thing I would like to put forth to you out there in the audience: if you cannot hear our signal, or if there is any impediment to the signal, either with the video or the audio, you can call in here, 679-7777, 845-679-7777, and you can directly tell us here at the studio, not that we can actually rectify the problem, but it
We
does
can
help us.
document it.
But it does help us document it, and if you really want good quality Channel 23 public access, don't just call here, call the supervisor's office and let your voice be heard that our local access TV station needs repair and care. Okay, and that's what I have to say about that. And so without further ado, I'm going to put Bob Lavaggi, come on Bob, into the frame here, so you can stand with me for a second. And say hi, Bob.
Hi.
And we have a video clip that he put together, and cue the video clip at any time.
Okay.
Here we go.
A clock is an object with a regular moment. The minutes on your clock are equal and each has 60 equal seconds. Cesium oscillates the same amount each second. Nature is full of regular incidents that are clocks, though they are less useful to us. The moon orbits Earth approximately every 28 days, but its orbits are punctual, making it a clock. Io orbits Jupiter approximately every 42 hours, but its orbit is punctual, making it a clock. The advantage of these clocks is they are large and can be seen from each other's distant location. Each clock appears to be moving slower from the other clock's location when they are separating. This manifestation suggests Einstein's special relativity. Clearly, time appears to be relative to speed. The same clocks appear to be moving more rapidly from the other clock's location when they are converging. Clearly, time appears to be relative to speed. Galileo's principle of transformation is consistent with this faster or slower variation in time between moving clocks. Einstein is silent on this faster manifestation. His silence begs for reconsideration of special relativity. Consider a cesium atomic clock on Io that is transmitting a regular pulse to Earth. Because atomic clocks are susceptible to gravity and acceleration, the pulse might be as much as 1/millionth faster or slower. This does not matter because the pulse will be regular and punctual. If Earth receives 151,300 pulses while Earth is at rest with Jupiter, then it will receive the same amount of pulses while Earth is separating, but it will take approximately 15 seconds longer on the Earth clock. This is consistent with Io appearing slower to the Earth clock and our moon. The moon would appear 4 minutes slower per 28 days as viewed from Jupiter. If Earth received 151,300 pulses while Earth is converging with Jupiter, it will take the same amount of pulses, approximately 15 seconds less, to present themselves at the Earth clock. This is consistent with Io appearing faster to our Earth clock and our moon. We can approximate that we are converging with the Jupiter clock around 66,000 miles per hour. If we factor in special relativity at 66,000 miles per hour, the predicted time dilation during separation would be 1/1,000,000th, give or take a bit. In other words, no measurable effect. When it comes to Earth converging with Jupiter, Einstein did not furnish us with a mathematical instrument that speaks to the apparent evident increase in the rate of these reference clocks. If the two clocks were separating faster than the speed of light, Einstein and Galileo would agree that both clocks would be going backwards from the other viewpoint. But let's get real. If you were looking back at a colossally bright pulsing clock and were separating from it faster than the speed of light, you would not see the bright pulsing clock. Looking forward, you would be coming up on the back end of the pulse that was ahead of you. That would not be the past. It would be a new moment of now, where you and the back end of the light have never been before. You would be between the future and the past, where you are now. You would be in proximity to a minuscule trickle of light from the past, which is where you are now when you look at starlight. That trickle of light does not express the incident that created the light. We can still have time travel in our imagination or in literature. Einstein should have gotten the Nobel Prize in Literature.
Mike's up. You're on.
Okay, so that's some pretty heady stuff for a short clip for us civilians out here. And one of the things that I was trying to formulate a good question around is, all right, well, let's start with the illustration. You know, we have the Jupiter and one of its moons, and Earth and the moon, and you're showing the precession or the
Yes,
movement
around.
relative of the moons, and you know, you know, I was really stretching my head here a little bit. This is the second time I've seen this video clip, and so what I'm trying to elicit is the differential. Why would we perceive a quickening or slowing of time relative to each of these, you know, whether it's the you know, Jupiter or Earth? I mean, I don't know if that's a good question, but
No, that's fine.
yeah. What's your thought on that?
Well, the reason we can see Jupiter and the moon Io of Jupiter is because of light. The light reflects off of those two objects and comes through space, and we see the light. Now, there are times when Earth is moving away from Jupiter at 30 kilometers a second. During that moment, the light takes longer to pass us because we're moving away. And that is evident in the evidence of the Jupiter experiment. That experiment was done by Philip Romer 400 years ago. And when I spoke to Bob Berman, I asked him if we could do the experiment now just to confirm the experiment that was done by Philip Romer. And Bob Berman said, no, that's silly. I guarantee you that that is the case, that you will get those same results that Philip Romer got. So that is the empirical evidence that the clock, the Jupiter clock, which is a perpetual, continual timepiece,
looks different to us because we're moving. It looks slower when we're separating and faster when we're approaching, which is exactly what...
All right, now this is a physical observation.
Yes.
So we're looking at the orbit of the moon, and when we are ascending towards it, it looks like to be moving at one speed.
Faster.
And then when we are receding from it, it looks to be moving at a slower speed.
Correct.
And this isn't just a subtle difference, it is really quite easily measured. Well, at least it is measurable with technology available to astronomers 400 years ago.
That's correct.
All right, so how much of a differential would that movement be? Clocking the movement of the, you said 4 minutes? Is it really that much, or?
Well, if we're...
From extreme to extreme. Right.
Well, Io goes around every 43 hours, or somewhere between 42 and 43 hours.
Okay.
But it's, whatever it is, it's exactly the same every time.
Relative to itself.
Relative to itself.
Right, okay.
Yes.
But relative to us...
But we're getting a 15-second variation over 43 hours.
Well, that's a lot.
15 seconds, 43 hours. It's measurable, as you said.
No, that 15 seconds of difference
Over 43 hours.
is still very big observational to clock.
It's unequivocal.
That's I didn't realize it was it's like that's like saying, you know, a difference of over 43 hours, 15 milliseconds.
Oh, no.
And I only say that because that's still measurable.
Right. Well, 15 seconds
but
is...
15 seconds...
That's substantial.
That's what I mean. That's a big difference. That's a big difference. Okay. That now illustrates in my mind what the whole gist of that part of your demonstration or video was. Any thoughts? Where to go with that?
Well, I mean, without a question, I would just be repeating what was already shown.
All right, well, let's take it to Einstein now.
Okay.
Einstein was silent about something. I failed to make a good enough mental note because I got hung up on the clock thing.
All right.
So where were we going with that when Einstein didn't comment on...
Right. Well, I should make a mental note that the presentation may have gone too fast for you to absorb it at the rate that the
well, no, it's also the pressure of doing a show. I'm trying to make mental notes, so
The camera's going out.
Yeah, while the camera's going out. So,
all right, all right. The essence of special relativity is that light always passes the observer at the same speed.
Okay, that's where I now. Yeah, okay.
And
Thank
so, if the observer happens to be moving away from the source at 30 kilometers a second, Einstein says the light still comes to Earth at the same speed. And I say, well, look, the evidence shows that it's passing Earth more slowly by 15 seconds. And of course, Einstein can't defend himself at this point, but the physics community is defending his principle. And what I've gotten from many physicists, which is very amusing to me, they say, oh no, you can't measure light in a stream like you do in your experiment. You have to measure a pulse of light. And if you just measure a pulse of light, then you would see that Einstein was right. I don't accept that at
Well,
all.
that's silly.
Of course it is.
That's not demonstrative of anything.
That's correct.
All right, so we have empirical evidence from the scientist again, 400 years ago?
Carl Philipp Romer.
Carl Philipp Romer, I've heard the name, but I wasn't really familiar with his work. From 400 years ago, having definitively measured up to Bob Berman's standards, okay, that the light coming to us or receding from us, reflected from Jupiter, has a 15-second variation in a 43-hour period. All right, now in my mind, that's a big variation. That's a substantially measurable variation. And the only way that can be explained is that our visual perception of light from Jupiter, depending on where we are oriented in our relative orbits, will give us either receding light or accelerating light. And it can't be specially relative. It can't be because we are the observer. We are ourselves not in a fixed position, and this difference of measuring the light demonstrates pretty solidly that it does not move at the same speed, regardless of your orientation.
Regardless of the speed of the observer.
Of the observer.
Right.
Right. So you've got a very strong argument that has been largely sidestepped, not answered to directly, or have you gotten some good feedback directly?
No, I have never gotten substantial feedback that I'm satisfied with. What happens in conversations with physicists is they say, let's put your experiment aside because the principle of relativity is that light is always constant. And the whole theory of relativity is based on that principle. And the principle works. Therefore, there must be a problem with your experiment. And you know, they have the establishment on their side. They have hundreds and hundreds of textbooks.
All right, let me just attack that thought for a second. So the answer you get is that the principle works, but the evidence.
My evidence is never.
It's not your evidence, though. I mean, the evidence that we have here is 400 years old, and even Bob Berman says that you can repeat the experiment and you'll still get the same results. So that's hard science. Hard science, folks. Hard science is when you have a demonstrative experiment that provides you proof reliably and repeatedly in subsequent performances of said experiment. That's where you have a real observational, hard, old-fashioned. It's not a model. It's an experiment that gives you a proof, that gives you evidence of something. And what we're talking about now is a principle. Now, principles. What are they? Let's in science. Let's give me just for the benefit of the audience and me a little bit. When these physicists says, but in principle, the theory works.
How does it work?
How does it work? I mean, what's there? The opposing team.
Right.
What do they say?
Well, I mean, first of all, principle is a word, and it may mean something different to me than it does to the scientific community. But when Einstein submitted his theory in 1905, there was an experiment which confirmed that light is constant with all observers. And that was a compelling argument. The experiment was done by Michelson and Morley. And that experiment was not able to pick up this differentiation in speed, light speed, that the Jupiter experiment does pick up. And Einstein and all of the subsequent scientists grabbed onto this notion, embellished with all of the mathematics of special relativity, and within its own context, it's very cohesive and logical. So at this point, they are holding on to that experiment, and as they say, all of subsequent science is based on special relativity, and everything works. Therefore, the Romer experiment must be an anomaly. Now,
all right.
You follow what I'm saying?
I have to stop you right there,
Yeah,
because you came up with the everything word. Everything works. And that is always a little red flag for me when it comes to science.
Me too.
And again, this sounds almost like dodging the point kind of an argument from the physicists, that everything works. Everything works meaning what? I mean, how are they being the physicists, how are they rationalizing such a blanket statement when everything works? I mean, everything works. Yeah, well, we're in a reality, right? And we are doing with what tools we have the best we can to measure this reality, right? For truth, right? This is the real point of science is truth, right? I mean, I can think of things that work that shouldn't, you know. But getting back to Einstein, and let's shift it to the puppet here for a second, because you know we're already killing our hour.
All right. Well,
because we have way too much fun with this, folks.
Yeah.
All right. So you made Einstein here.
Actually,
let me just stop here. I love Einstein. I love your Einstein. I mean, what really gets me the most about this puppet or mannequin is he really feels like Einstein standing there. I get, you know, the kind of absent-minded professor kind of a thing, and the disheveled look of it. I mean, how did you manage to capture it so well? I mean, it seems like you were on a mission with him.
Well, I mean, I was a puppet artist, and this is just another puppet.
Okay.
And the idea of puppets is to try to breathe life into the puppet. So I managed to do that, I guess.
Here, you know, absolutely.
Really.
Now, what are we looking at here with the ball?
What I wanted to say, we actually covered everything that I cover with the puppet in our conversation. But I'm happy to go over it again with the puppet.
Okay.
I do want to give some reference to this. I was selling my book, Einstein on the Carpet, and it's a hard sell. So I built this setup and brought it to the planetarium in New York City and set it up on the street. And it did what it was supposed to do. Here's the book.
There you go. Great. Keep it up.
Yeah.
No, that's fine.
Nope, you can stay right there.
Stay right there.
Okay. So, what happened, people would be going to the planetarium and they would see me standing outside with Albert and the sign and the softball here. And they would come over and I would have long conversations. Sometimes I would stand on the street for 5 hours on Saturday or Sunday and speak with hundreds of people who occasionally bought a book. And what I would tell them, I would first refer to the writing there, The velocity of light in a vacuum is the same for all observers moving relative to each other. That is Einstein's principle. And then I interpret that and explain, as we did last week, that means if you're going towards the light or away from the light passes you at the same speed. And that is contradicted by the Romer experiment, which you saw on the video.
Oh, okay, now that's when I think I started interjecting last week about the red shift, blue shift phenomenon. And in terms of audio phenomenon, because I'm a musician,
Yes.
I worked a lot with sound. We often have to deal with echoes and things of that nature, which is the sound being, bounced off a wall and things like this, and it comes back to you, or this kind of thing. So we're, as a sound technician, I'm very aware of the speed of sound, really, because depending on how far that wall is, it'll give you a longer or shorter duration for the echo.
Yeah.
Now, in that principle is the Doppler effect. And in sound, as an analogy to light, when you have, say, a race car, a Formula Ford race car, right, and it's coming up the track towards us,
Higher pitch.
it has a higher pitch. And so when it passes us, the pitch reaches a crescendo and then a decrescendo. The pitch appears to drop in frequency, so it becomes a lower pitch as it recedes away, and as it's aceding towards us, it's a higher pitch, and
Right.
and the pitch seems to gain a little bit of rise even from the far distance. So, or maybe not. I don't know. That could be in my imagination.
Certainly the volume would be louder
The
because it's
volume
closer.
changes as it close to the volume. So
I
I'm
don't
not sure
think-
about the pitch.
I don't think the pitch changes.
Yeah.
What's most interesting to me about that, you gave a demonstration of a race car, but I love the jet plane or the airplane.
Right. We all know that sound from summer times as kids.
Right.
The lone airplane.
And in
Yeah.
your case, the pitch shifted fast.
Right.
And the airplane is a slow shift, and so I'm always fascinated by that slow pitch. And I would say that's because the race car is going right past us, so it's here and then it's there.
Right.
So the pitch changes very fast. The airplane is out there and it's way off in the distance and you hear it. And it just, as it goes past us slowly from a distance, it drags out that change in pitch.
It's in a sense, it's a diffusion.
Is it? Yeah.
Because
yeah,
of the medium.
Because,
the medium of air being the medium that transmits the sound in the first place, because theoretically, without in a vacuum, you do not have sound.
Yeah, that's right. If it was a vacuum, we wouldn't hear the plane. But at any rate, that as a side has always fascinated me, that slow curve in pitch. So we're connecting this to light,
Yeah. Now,
which Doppler shifts also.
so it's the same. It's the same. Doppler is afforded to both
Light and sound.
and sound.
That's correct.
Okay, I was just.
So when a light source is coming towards you, it shifts blue. When it's moving away from you, it shifts red.
Okay, now here's an anomaly for you. I'm not sure which publication I read this in, but I understand that there is a few classes of stars that redshift is red, and yet it is measured as coming towards us. Have you encountered this one yet?
I have not encountered that.
That's something to look into. See, I'm gonna go back and see if I can find some references on the internet. You know, I'll poke around. And it was relative. It was the discussion was relative to dark matter and the idea that space is a thing, and that groupings of stars, planets, systems are seemingly moving like in eddies. You know, that it's not like, you know, in the Big Bang theory, there is a singularity, came from nowhere. We don't know how that even happened, right? So there's a few questions about that. It explodes because it wants to, I suppose. And then from all of this, our measurable universe has sprung. And if it were a singularity, the thought goes, well, then everything is moving away from a center point, so we should be able to find that center point because of the relative motions. And I think that's where parallax comes in, is relative motions and positions from one point in time to the next. Problem is that the astronomers looking into this situation, haven't been able to really find at least a common enough directivity of all this motion to point to where the singularity began. So that's one problem, because they've got eddies, which, you know, if you look at the circulation of water in a stream or whatever where the eddies occur, I can see, well, that kind of stands to reason. But then you have situations where you have galaxies literally colliding with each other and going through each other. So there's a lot of questions to come up with that can argue against that idea of a singularity and the Big Bang that created everything some 14 billion years ago, however they measure that. Where am I going? I'm not sure.
Well, let me just comment on what you said. First of all, I got involved in the speed of light and measuring the speed of light, and I have stayed very focused on that issue because that is the principle of special relativity. So I have some idea about astronomy,
right?
But I don't have tons of data on it. So I'm really not an authority on all of the details of astronomy. But from what I understand, it appears that we are in the center of this universe, that the redshift is the same distance in that direction as that direction. That. It appears to us as if we're in the center. And that is because, the astronomy community says that it's because the stars are moving away faster. And as I said last week, I think that it's because when you get that far away from us, the light just loses steam, and so it's the farther away it comes from, the redder it is by the time it gets here. That would be consistent with the notion that it appears that we're in the center of the universe that we can see.
Actually, you may have just answered the conundrum for stars that have a redshift but are measured by a third method, perhaps, second or third method, as to be coming towards us as opposed to coming away from us.
Actually,
so what you might be identifying here is an answer to that phenomenon that has confused. It's only been because of the better measuring equipment in the past, say, 50 years that this anomaly has been observed. And maybe it's not the motion of the star, the light source, so much that's defining redshift and blue shift in very, very distant objects, maybe it's the light is just slowing down because it's tired. And I think that is probably the most attractive answer yet.
Well,
to me,
it's the one that makes sense to me. But I have to remind us both that astronomers, there are thousands and thousands of astronomers who've gotten their doctorate degrees in astronomy who are working on one theory. So it's probably a little distasteful to them, for me, who doesn't have a degree in astronomy, to be posing an answer to your question out of my back pocket. So I want to acknowledge just in a moment of humility here.
Sure.
However, having expressed that moment of humility, I think that the universe is full of all types of debris and all types of matter and all types of gravity and different temperatures and different types of mass, visible, invisible. And there's no reason to believe that there are not places out there in the universe that are dense, and that any light coming from the other side of that dense matter gets worn out passing through the dense matter. It just gets trapped in the mass, it gets trapped in the gravity, it gets worn out. It finally gets through and it gets to us, but it's worn out light. So that would be a quick hypothesis from a person who is just following my instincts.
Well, in a kind of a big way, it's all most of us can do is follow our instincts. And if something doesn't feel right, I know for me, if something doesn't feel right, as a gut reaction or as an intellectual reaction, that's when I start formulating questions. And before I can formulate questions, I have to study it.
Yeah.
And
which is what I did with special relativity. I
Yeah.
studied, read 20 different textbooks on the subject, and curiously, the same phrases appear in every textbook.
Yeah.
So it's like carbon copies. It's not original thinking. That was a red flag for me, that subsequent writers just quote what was said before.
Now, you've been I love this, focused on light, and yeah, and I've always been fascinated with this thought, this Newtonian science of objects and orbits of planets being predictable.
Yes.
From closer to the star, the smaller the planet, or maybe there's some room for variation in there. Maybe there are smaller planets, but the planets themselves and the order of the orbits could be a little bigger relative to each other,
Mm-hmm.
or smaller. Not a hard and fast fixed rule there, but the further out you get is when you will find the larger planets,
Mm-hmm.
and that there is a predictability to this with looking at other solar systems relative to ours. And then moving right along with more of these Newtonian ideas about gravity, the object of the apple falling on his head and making him think about gravity. Did Newton, I'm not that I should ask you, who coined the term gravity?
I don't know who coined
It's a
that
grave
term.
question.
That, you know what, I'm going to find that out, and I'll let you know next week, folks. But we do have, like textbook information, pounded into our heads about how mass is a kind of a determinant factor in gravity. So the greater the mass, the more gravity.
It appears that way.
It appears that way.
Yeah.
And that, according to Newton and Einsteinian calculus, there has to be X amount of mass in the universe to hold it together.
I don't know about
And,
that.
well, I don't know about it either.
I don't know whether the universe is being held together. The universe implies that the universe is finite and it has an end, an edge.
Well, let's take it to the solar system. So the solar system holds its uniformity
Yeah.
because of the relationships of gravity in all of these orbits and movements.
That's the theory that I would go with until there was another theory which was more persuasive.
Well, I just wish I had that steel trap memory some of my friends have, where they can just pull up and quote people and places and things. But another idea that I've encountered that is that in Einstein's model of a unified field theory, that there has to be this X amount of mass in the universe for everything to work, right? And this, I think, was built on Newtonian ideas, right? And then now, with the last, say, 100 years of ever greater precise measuring instruments of our cosmos, that X amount of mass isn't there. And this is where dark matter comes into play.
Mm-hmm.
It's not there. There are scientists saying, well, Einstein's theory of not general relativity, or unified field theory.
Gravity is general relativity.
Okay, of general relativity has a flaw, and his calculus doesn't add up compared to observable and measurable statistics that they're looking at. 90% of the mass predicted to be there isn't there. It's almost entirely all space. And somehow this impacts the general relativity. I don't know have you encountered that thought?
I've not looked at that carefully.
I should finish the thought and carry it on to the next point. So,
Yeah.
Right, so the quantum physicists, they come in about 80 years ago, 100 years ago, 80 years ago, and they started hammering on Einstein right from the beginning. They were hammering on him right at the beginning. And there's now, you can look it up online, there's a lot of information on it now, called the electric universe model.
Mm-hmm.
And in the electric universe model, it dispenses with the requirement of mass to satisfy the existence of gravity.
Mm-hmm.
Because the quantum fellas are now saying, okay, well, Einstein had a lot of it right, but he did have errors, or maybe some significant errors that he went to the grave knowing he had.
Mm-hmm.
That was, one of the things I've read about Einstein is that he went to the grave dissatisfied with his own, not being able to finish and make something work in his equations. But they're saying that if they plug in elements of the electric universe model and remove the requirement of mass, and and attribute electricity as the determinant factor of gravity, then you have a truly unified field or general relativity that works. And that's kind of the thing that I've been looking at.
I've looked at a bit of this.
Yeah.
And I really am not qualified to make an educated comment on that.
Right.
So that is something that I
Well, let me
We'll
wrap
need
it
to
into
look
light. Let me wrap it into light because,
Yeah.
you know, there are things about light that do fascinate me. And one of them, now I'm not sure if this was an experiment that I can describe correctly, but there is a double blind or a double slot, a slit experiment with light being passed through it, and then it demonstrates what either looks like
A wave or a
a
particle.
a wave or a particle, thank you. And that's what becomes real interesting to me, because if Einstein's proposition that the velocity of light in a vacuum is the same for all observers moving relative to each other to work, then light would not be a linear phenomenon. It would have to then be an omnidirectional phenomenon. It would have to be a waveform. It would have to be something that is not linear.
Well, all right. So I see what you're saying. I encountered this double slit theory 35 years ago, and I never was comfortable with it. And I've given it a lot of thought over these last 35 years. They reference light either as a wave or as a particle. And when they flow light at the two slots, the two slits, you get the wave pattern on the other side. All right, so that sort of confirms that it's a wave. When they cover one up, they don't get that wave pattern, but of course, light is only going through one hole. So you don't get the interference on the other side of the slits. But the big objection that I have is this notion that light is a particle. That notion, a photon, a particle, of light flying through space, I don't buy that at all. Because if you think about it, how do you get a particle of light? If you have a light and you open the shutter if you open the shutter for a second, you get 186,000 miles of light in that 1 second. You've got a chunk of light that's 186,000 miles long.
Okay.
Now, if you cut that down, if you divided that by 186,000 and just had 186 thousandths of a second, that's how fast the shutter went, you would still have a mile of light.
In a second.
No, in 186 thousandths of a second, you have a mile of light. If you have a second, you have 186,000 miles of light.
I see.
So if in 186 thousandths of a second you get a mile of light, then how fast does that shutter have to close in order for you to get a particle of light? You have to divide how long is a particle of light? Is it 1 inch long? In order to get a signal of light that was 1 inch long, how much would you have to divide that 186 thousandths of a second into in order to reduce that mile to an inch of light?
You're almost talking about the speed of an electron. I mean, it's like
Yeah, well,
you can't.
but
You can't. What I'm postulating here is there. It's a mechanical impossibility. to have a shutter speed that fast.
Yes, of course it is. So what are they talking about when they say they're shooting a particle? They say that as if they have this particle of light, bing. How do they get hold of it, and how do they send it without sending a stream of light? If they get an inch of light after such a vast amount of division. Don't forget, you get a mile of light if you divide the second into 186,000 little parts.
Right.
So I don't buy the notion that there's any such thing as a particle of light. It just isn't. Whatever the phenomena is that they get, I'm not arguing with the phenomena, I'm arguing with their idea that they think they've got a particle. Now, there are millions and millions of physicists who do this experiment and teach this experiment. So for me to make this point in the face of all of that confirmation of opinion is
It's an uphill slog.
it's an uphill slog.
Yeah.
But okay, here I am. I'm expressing myself to you. It's my idea, and it's a relief to say it.
Yeah. No. Well.
And I wait for an explanation of how they know they've got that particle of light. I want an explanation for that.
Well, here's another problem for Einstein, and if the velocity of light in a vacuum is the same for all observers moving relative to each other, so in other words, we really shouldn't be seeing Jupiter with a 15-second variation in the observable orbit of its moon, just because it's either positioned in one part of its relative orbit to us or the other. See what I'm saying? So that shouldn't be happening, according to this.
That's correct.
Okay? I had a thought about that. Darn. So that, in my mind, is demonstrative of a thing, light as a thing. It's more than an object, though, because an object, when I think of an object, we think of a particle, we think of a thing that can be stationary. But when we're dealing with phenomena of light, we are dealing with something that can never be stationary.
That's right. As soon as it exists, it's moving.
Right.
Yeah.
Its very existence is in only one, I want to say one dimension. For like time is a dimension.
Mm-hmm.
So perhaps light is a dimension. Right. So we have the three physical dimensions. Right. We have the up, the down, the sideways,
and time,
and time. And now we have light factoring in as another element to work with, which is neither a physicality, though you can see it, you can't. Well, you can feel light too. I mean, it has.
Well, I think that light is physicality, and you can measure light, you can measure it. You can't measure. You can't measure length. You can measure light. Length is a measurement, but you can't measure it. You can't prove that a measurement, that a foot is a foot. You can't. I can't prove that there's a cubic foot of space here. That's a dimension. You can't measure it. But light, you can measure it. You can see it, and it causes an impact. So I would say light is physicality, as opposed to dimension, which is conceptual.
Well, we've eaten up another hour. That went quick.
Went very
It
fast.
wasn't even faster than the last time. We're getting used to this. Thanks for coming, Bob. And Bob Lavaggi, he's got serious questions for Einstein, but dead man tell no tales, so we have to deal with his successors. And thank you for watching Channel 23, WATV, Woodstock, public access, and I'd like everybody to have a really great week, and keep tuning in, and let your town board know that you love your station and you want to see better programs coming out here, and all that kind of good stuff,
And better support for the programs.
and more support for our programs. And so, signing off until next week, the Conant Show, George Conant, Bob Lavaggi, and our engineer, Paula Glora Barton.